Hello friends, the next lecture. So in the last lecture we looked at conduction heat transfer, the heat conduction equation derivation, and we looked at the various simplifications of the heat conduction equation, and we also looked at how to solve the steady state one-dimensional conduction equation with constant properties and no heat generation. So we found that you get a straight line temperature profile and you can define something called a thermal resistance using the electrical analogy with temperature difference as the analog to potential difference and the heat flux as an analog to electric current. And we were able to define something called a thermal resistance, which was defined as L by Ka for a planar geometry. And we were able to extend this for including the convective heat transfer on one of the walls or both the walls, or we were able to also account for a multi-layered wall with multiple values of conductivity and thickness, right? In today's class, we will try to look at the conduction equation in one dimension, but for a cylindrical system. So we will be looking at hollow cylindrical shells, which are examples of, for example, pipelines that are carrying steam. They are hollow cylindrical shells. On one side you have the steam, and on the other side you have the surrounding atmosphere, and the heat loss through the pipe can be calculated using this expression. Similarly, electrical wires, they are generating heat from inside because of ohmic resistance and ohmic heating, and this heat needs to be transmitted through the electrical insulation that is there. So the insulation that is there needs to serve as an insulation for electricity, but should be able to allow heat to pass through. So in today's class we'll basically look at the factors, the equations, as well as the characteristics of the solutions for cylindrical systems. So let's move to the other screen. So now let us look at a cylindrical system. So let's take this as a cylindrical system. Okay. This is the cross section, and the length is very large in this direction. And let's say this is radius, inner radius, and this is the outer radius. So the inner radius is, let's say, R1, and outer radius is R2. Right? Let's clear this also. Okay. Now, if we try to look at the energy conservation in a cylindrical shell like this, so let's take a small portion of the shell here. Okay. Now, let's for the moment ignore the variation in the theta direction, that is in this direction. We'll only consider the heat conduction equation in the radial direction, and we'll write the equation for radial and the z direction to make it indicative. Finally, we'll be solving only a one-dimensional case for radial direction. So let us look at this. So this is, let us say, q dot double prime r at inner radius of the shell. So let us be taking a small shell out of that, and that is being blown up here. Okay. This arrow will interfere, so let me remove this arrow. Okay. So this is basically what we are looking at, and let us draw the hidden surfaces also here. So the heat flux here would be Q dot R plus delta R. Okay. Similarly, you might have Q dot double prime Z here, and on top Q dot double prime Z plus delta Z. Right. So in the same way as we did for the previous problem, we can look at this. So if I take a shell which is not just for this delta theta but also going through the entire cylindrical shell, then the volume of this would be basically 2 pi r dr, which is the area of the let's say top surface or the bottom surface, the cross sectional area, multiplied by delta z, where this is delta z and this is delta r, right? And the inner radius is of course r, and this is r plus delta r. Now this will be the elemental volume dV. Now if I take this and write the first law for this control volume, then I will get del by del T of rho into 2 pi r dr dz multiplied by CVT. Okay, so the bracket should include all of that. This is the left hand side, and this will be equal to, now because we have written a two-dimensional case, there will be only 4 fluxes that will be there, which will be Q dot R into the area, which is 2 pi r dz. This is the heat coming in from this one, and the one that goes out there has a different area, so that is 2 pi r plus delta r into dz. So we'll be writing that as minus Q dot double prime r plus delta r multiplied by 2 pi into r plus delta r multiplied by delta z. So that's the heat flux into area in the radial direction in and radial direction out, plus similarly for the z direction you would have a Q dot double prime z minus Q dot double prime z plus delta z. Both of them have the same common area, which is 2 pi r dr. Okay, so this is the heat flux. We are neglecting the heat generation term in this case. If you want, we can also include that. We'll then put it as Q dot triple prime generation multiplied by the volume, which is 2 pi r dr into dz. Okay, so I'm mixing up dr and delta r. So this basically is delta r delta z, and similarly here it's going to be delta r delta z. Okay, and similarly wherever we have written that. Right. Okay, so this is your equation. Now we will apply the Fourier law of conduction to the Q dot double prime terms. So your Q dot double prime at any radius or this one is going to be equal to minus k del t by del n for that particular direction. So for r this will be del t by del r, and for z it will be del t by del z. So we put that and substitute it in the respective location. So what we will get is del by del t of rho 2 pi r delta z into CVT is equal to, so we'll get the 2 pi delta z that will come out of this. So 2 pi delta z is common to both this term and this term, so that can be taken out. So you will have a q dot double prime r into r and q dot double prime r plus delta r into r plus delta r multiply. So the q dot double prime written as k del t by del m will then give me the equation. So this multiplied by k r del t by del r at r with a minus sign and minus k into r plus delta r into del t by del r at r plus delta r. Okay, so that will be that term. Similarly, minus 2 pi r delta r, that's a common area, and that will be multiplied by k del t by del z minus k del t by del z. So this is at z and this is del z at z plus delta z. So this will be the second term, and the third term will of course be q dot triple prime generation into 2 pi r delta z. Now we divide this throughout by the volume and adjust the minus signs into this, so these two terms get swapped, and similarly these two terms get swapped and the equation gets rearranged. So you would get, if I divide it throughout by the volume, I'll get del by del t of rho CV t is equal to 1 by delta r, 1 by r delta r, because you have a 2 pi delta z here. If you divide it by 2 pi r delta z, then you will have a 1 by r delta r that will come on the bottom there. 1 by r delta r multiplied by k into del t by del r at r plus delta r minus k del t by del r at r. Okay, so this, taken the limits as delta r tends to 0, is one part of the equation, plus similarly you will have this equation has 2 pi r delta r, so when you divide it by this you get a 1 by delta z, so you get 1 by delta z multiplied by k del t by del z at z plus delta z minus k del t by del z at z plus q dot triple prime generation. Now the first term is k del t by del r at r plus delta r and k del t by del r at r. Okay, there is an r missing here, and this will be r plus delta r. Okay, so okay, right. Now this is kr. Again, mistake here. This is r and this is r plus delta r. Okay, so this becomes actually k into r plus delta r multiplied by del t by del r. So this k r del t by del r at r plus delta r, and this is k r del t by del r at r, divided by this, taking limits when it tends to 0, it becomes equal to 1 by r del by del r at k r del t by del r. Okay, plus similarly this will be 1 del t by del z of k del t by del z plus this term. So this is your equation. So the final equation, we can write it cleanly on the next page. So this becomes del by del t of rho CV t is equal to 1 by r del by del r k r del t by del r plus del by del z of k del t by del z plus q dot prime generation. So this is your two-dimensional heat conduction equation with r and z directions. Theta direction is taken to be circularly symmetric, so you get a two-dimensional heat conduction equation. Had you looked at the variation in the theta direction as well, when you looked at this control volume, oh, you have come very far. Yeah, when you looked at this control volume, if you also looked at the theta variation, then you would have got del by del theta, which will be the complete three-dimensional equation. Okay, so now we have a two-dimensional equation. If we write this for one dimension, when the z direction is very long, like in the case of steam pipes or in the case of electrical conducting wires, so this term will drop out, and when there is no heat generation, for example, in the pipe there is no heat generation. Similarly, in the insulation of the conducting wire, there is no insulation. It's in the conducting wire there is a heat generation, but that is not part of our domain. We are only looking at the shell, which is the insulator. So this part may be the conductor, but the insulator is here, which is not generating heat. So this term will drop out and this term will drop out, and we are looking at steady state, so this term will drop out. The only thing that will remain is this term. So it becomes a ordinary differential equation because there is only one independent variable, and if I take k as a constant, this k will also drop out from here. So then you get 1 by r d by dr of r dt by dr equal to 0. And since it's equal to 0, 1 by r would never be equal to 0 because r is all finite. So this will also drop out of the equation. So you will get only this part, d by dr k dt by r dt by dr equal to 0. That is your governing equation that you will need to solve. So let's start solving that now. So for a cylindrical shell of radius r1 and r2, I'm drawing it too small for my finger to be able to write this right, and this of radius r2. Okay, and let's say the temperature on this surface is T1 and this temperature on this surface is T2 are the two boundary conditions, and your equation is d by dr of r dt by dr equal to 0. So now if I integrate this the first time, you get r dt by dr is C1 or dt by dr equal to C1 by r. Okay, so I'll just erase this and write it here. Now if I integrate this a second time, you get a logarithm for the integral of this one. So you get t is equal to C1 log of r plus C2. Okay. Now for the two boundary conditions, I have r is equal to r1, t is equal to t1, and r equal to r2, t equal to t2. So let us apply them. At r equal to r1, t equal to t1, which means t1 is equal to C1 log r1 plus C2. And similarly, r equal to r2, t equal to t2, you get t2 is equal to C2 log r2, sorry, C1 log r2 plus C2. So now you have two equations and two unknowns, C1 and C2. You solve for them. So you get, if you subtract the two, you get T2 minus T1 is equal to C1 log R2 by R1. Okay, so which gives you C1 is equal to T2 minus T1 by log of R2 by R1. So this is one constant. If I substitute this into this, I get the second constant. So that gives me T1 is equal to T2 minus T1 by log R2 by R1 into log R1 plus C2, which basically means C2 is equal to T1 minus this. C2 is equal to T1 minus this whole thing, T2 minus T1 by log R2 by R1 into log R1. So this is the term that you get. So substitute both C1 and C2 into the original equation of solution, which is this one. You get the temperature profile. So what do you get there? So it gives you T is equal to T2 minus T1 by log of R2 by R1 into log R plus T1 minus T2 minus T1 by log R2 by R1 into log R1. So I can rearrange this. I bring this T1 to the left hand side, and then you have only T2 minus T1 by this. I bring the T2 minus T1 also to the left hand side, so I get T minus T1 by T2 minus T1 will be equal to, there is a log R and a log R1, so I will get a log R by R1 by log R2 by R1. So this is your temperature profile. So you get a logarithmic variation in the temperature profile, and that comes out because the area itself is a function of radius, and that's the reason for that. So if I take the derivative of this dt by dr, I already have it in the solution here. So if I have dt by dr is going to be equal to C1 by R, and therefore I can take R dt by dr is equal to C1. And what do I need? I need the heat flux, which is q dot double prime at any radius is going to be equal to minus k dt by dr del T by del R at R, right? So this is known, and so that will be equal to minus k times del T by del R at R, okay, is C1 by R, right? So if I use C1 by R, where C1 is given by this expression, then I get K by R into T2 minus T1 by log R2 by R. Okay. Now the heat flow through any passage, okay, any plane at any given radius is going to be equal to this multiplied by the area. So q dot double prime R, so this is, let's say, q dot is going to be equal to this multiplied by 2 pi R into, let us say, the length L of the whole domain, and if I multiply that by 2 pi R L, so this is q dot is going to be equal to this multiplied by 2 pi R L, then this R gets cancelled out and this whole thing is a constant, right? So you get a 2 pi Lk multiplied by T2 minus T1 by log of R2 minus R1, and that's a constant. So that is again a steady state thing. Any radial plane, the total amount of energy crossing will be equal to the total amount of energy crossing any other radial plane. So there is no energy accumulation between any two radial planes. So that is the definition of steady state. So that is making sense. So let us use that now, and we can get the expression for the thermal resistance. So what do you get? You get q dot is equal to T1 minus T2, the negative sign absorbed into this makes T2 minus T1 into T1 minus T2, divided by log of R2 by R1 divided by 2 pi Lk. The 2 pi Lk that was from the numerator, I brought it down to the denominator. So now this becomes your thermal resistance. The remainder of the expression is familiar. This is akin to your current, this is akin to your potential difference, and therefore this is akin to your resistance. So in the case of radial system, the resistance between any two radii R1 and R2, let's say this is R1 and this is R2, and the temperatures here are T1 and T2, then I get this RTH, which is equal to this value. Okay. Now, in the same way as we did for planar systems, suppose I say there is a T infinity here and there is further resistance, okay, where we can write T2 minus T infinity is H into 2 pi R2L, which is the surface area at the radius R2, multiplied by T2 minus T infinity. Then this can be written as so the same Q dot is going to go out of the other side, so this Q dot is also equal to H into area. So the amount of energy coming here is Q dot, the amount of energy going out here is also the same Q dot at steady state, so that will be equal to H into 2 pi R2L into T2 minus T infinity, which can be written as T2 minus T infinity divided by 1 over H into 2 pi R2L is the thing. So this is the thermal resistance that is caused by the convection on the outside. Now Q dot is equal to this and also equal to this, and that will also be equal to T1 minus T infinity divided by T log of R2 by R1 by 2 pi Lk plus 1 over H into 2 pi R2 L. So that is the third expression that you get. So the thermal resistances between T1 and T infinity get added together, this and this, in the form of this and this, and so you get T1 minus T infinity divided by the two resistances added together is the same heat flux Q dot. Okay. Now, there is an interesting feature about this thermal resistance, which is something we need to appreciate and understand. So this thermal resistance now is actually equal to log of R2 by R1 divided by 2 pi Lk plus 1 over H into 2 pi R2 into L. Now what you observe is that if R2 increases, this term is going to increase in a logarithmic way, but this term is going to decrease because 1 by R2 decreases as R2 increases. So if I try to plot these two, so let us say this is R2. What is R2? The outer radius of your insulation. Let us say if this is an insulation, and this is the heat generation or heat supplying region, which is maybe your pipe or your electrical conducting wire, then this is the energy going out from, and this energy will go through the insulation out. So this is the steady state distribution. So at the steady state distribution, I say that this term and this term contribute to RTH. So how does the first term contribute? Let us say if R2 equal to R1, then this logarithm is 0. So this first term becomes 0. After that it increases and goes in a logarithmic manner towards higher values. This is the way the term 1, which is basically a conductive resistance, changes. And this one is going to go like 1 by R. So you have a variation that goes like this. This is term 2. Okay, so the sum of these two will actually start from somewhere here, go to a minimum and go up. Okay, so this is the way the sum of the two terms is going to go, and it is going to show a minimum at some radius, which we call as R critical. Okay, so what does it mean? Starting from radius R1, which is the inner radius. So if I have a bare wire, electrical conducting wire for example, and I start insulating it, So the thickness of the insulation starts increasing from 0 to a higher value, or the radius of the total system is going to increase from R1 to some other value as R2 increases. Now at some value of R2, this resistance is going to be a minimum, and until such time that the radius is less than that R critical, the total resistance offered by it is going to decrease as you add more and more resistance. Normally you insulate in order to add resistance, but here it's counterintuitive. You add resistance, but the resistance is decreasing, and therefore the conductance is increasing. Okay, why is that happening? Because this term decreases because of increase in radius, and in this case below R critical, that dominates over the increase of this one, and beyond this R critical, what you expect is happening the way it should happen. So you increase the radius or you increase the insulation, and the resistance is increasing. So this critical radius can therefore be really critical one, because we think that we are adding insulation, but actually we are increasing the heat losses. But it can also be a blessing. Let us understand how. Now in the case of electrical insulations, that is when we have a conductor and when we have an electrical insulator that is surrounding it, we want this electrical insulator to prevent anybody from getting electrocuted or this voltage being contacted by anybody else. So it has to act as an electrical insulator, but at the same time this is the region where ohmic heating can happen because of the resistance of the conductor, electrical resistance of the conductor, and therefore the heat that is generated here needs to flow out through this. If it accumulates inside, then it can overheat the conductor and also damage the insulation. So it has to go out. So the electrical insulator, or what we call as an insulator, is in fact required to be a conductor, right? In that sense, adding more insulation, if it results in increase in conductance or decrease in resistance, it's a blessing. So it's good in the case of electrical insulation, but it is not so good in the case of, for example, steam pipe insulation, where you have steam that is flowing through this and you have resistance that's getting added, electrical resistance, not thermal resistance, that are getting added here. So if you add more resistance, if it increases the heat losses, that is bad there. So in the case of steam pipes, critical radius can adversely affect, but in the case of electrical insulation, it can positively affect. So let us look at the phenomenon of critical radius. So we said that the total radius is given by this expression, and so if I want to find out the radius R2 at which this RTH is a minimum, I need to differentiate this with respect to R2 and equate it to 0. So d by d R2 of RTH equal to 0 will give me one value, one expression from which I can solve for R2. That will give me the value of R critical. So let's if we do that, then actually I am not going to do the algebra here. I'll leave it to you to do as an exercise. So you will get R2 critical for a cylindrical system works out to K divided by H, where K is the thermal conductivity of the insulation. So if this insulation has a conductivity K, and H is the heat transfer coefficient for convective heat losses outside, then the ratio K by H is going to give you the critical radius. Let us now do a quick order of magnitude study. Suppose we are looking at electrical insulators. Normally we use polymers or Teflon or things of that kind that act as an insulator. So the conductivity is typically of the order of, thermal conductivity is of the order of 0.1 watts per meter Kelvin. And if you use, for example, glass wool or any such insulation, it can be slightly lower than that. It can go to something like 0.01 watts per meter Kelvin. So let us say K goes in the range of 0.01 to 0.1 watts per meter Kelvin, and H we'll study about it when we study convective heat transfer, but we can just get an order of magnitude. Suppose I'm looking at a quiescent atmosphere, stationary atmosphere, where no strong winds are blowing or no fan is on and things of that kind, then this H can typically have a value anywhere between 5 to 20. That's the range that you expect, quiescent with maybe slight amount of movement. This will be in watts per meter square Kelvin. So the ratio of the two will give you the critical radius of insulation. So the range of values of this therefore is going to be, the smallest is going to be this divided by this, and the largest is going to be this divided by this. So you will have 0.01 by 20, which is like 0.0005 meters, to 0.1 by 5, which is 0.02 meters. So this is 0.5 millimeters, and this is about 20 millimeters or 2 centimeters. So the size is in the range of half a millimeter to about 20 millimeters. That is typically the range of thicknesses of electrical conductors. So in electrical conductors, this critical radius is going to affect. But if I look at the steam pipes, the K is of a similar order, 0.01 typically, 0.1 is actually not normally used, and the heat transfer coefficient is, let us say, 20, so you get this in the range of so much. But steam pipes are typically of a diameter which is like 20 to 30 centimeters or 200 to 300 millimeters, which is well outside the range of the critical radii. So you don't really need to worry about the critical radius, because for steam pipes you will always be at a radius higher than critical radius. So in electrical insulations you will need to worry about the critical insulation, and keeping the radius less than critical radius of insulation is always going to be a good advantage. If it goes higher than critical radius, then addition of insulation is going to hamper the heat loss, and we need to prevent the hampering of heat loss. We need to actually allow the heat loss to happen, right? So we can use the critical radius as a friend in the case of insulation of electrical conductors. Now, in a similar fashion as cylindrical systems, we can also define critical radii for spherical system. The governing equation for spherical system, instead of R, would contain an R square. So the one-dimensional equation is going to look like d by dr. Here there will be a 1 by r squared d by dr of r squared dt by dr equal to 0, and therefore the solution, instead of a logarithm, would have a 1 by r, because when you integrate c by r squared, you get minus 1 by r, and therefore you will be using 1 by r in place of log r. So that's the way the solution will look at. And if you go ahead in the same fashion as for cylindrical cases and find out the expression for critical radius, r2 critical will be equal to 2k by h in the case of spherical systems, in comparison with k by h for a cylindrical system. Now 2k by h is not going to change the order of magnitude, but it will be in the same range of values. So again, this is going to be relevant in the size range of about 0.5 millimeter to 2 centimeters multiplied by 2. So which will be spheres of radius of 1 millimeter to 4 centimeters. Again, they are very small. Normally spherical insulations are commonly encountered in liquid natural gas tanks whose diameters are of the order of tens of meters. So this is nowhere going to affect. So any insulation you add is going to add to the resistance, and which is what you want in the case of those applications. So this is basically for this case of theoretical interest that I mentioned, that you also need to look at critical radius in the case of spherical systems as well. Now, the last topic in conduction heat transfer of steady state systems that I would like to discuss with the class is extended surfaces, also called as fins, and the system of extended surfaces or fins together constitute what you call as the heat sink. which is commonly used in electronic equipment to dissipate the energy that is generated in those systems. So it's important to discuss these as part of steady state heat transfer systems, because they are of very common use in engineering, and electrical engineers who study thermal science need to know about them. So normally whenever you have any equipment, like for example electronic chips, the CPU or the graphic processor chip or any other chip in the computer or mobile phone which needs to dissipate energy. Similarly, you also have electric motors that generate heat. You have internal combustion engines that generate heat. The heat from these systems needs to be dissipated to the surroundings so that the component that is generating the heat does not get heated beyond temperatures which they can withstand. So you need to increase the heat loss, and normally the heat loss takes place due to convection, and convection heat loss can be written, as we had written earlier, as heat transfer coefficient H multiplied by area multiplied by the temperature difference between the surface and the medium that is cooling it. Now this value of H depends on what kind of fluid and what kind of flow arrangement that we have maintained around the object that needs to be cooled, and depending on these and depending on the constraints on these, the values of H get restricted. Okay, I can give you simple figures. Say for example, if I am cooling computer chip, okay, so the computer chip can be either cooled using a flow of air, which is the most common thing, or if these are chips which are more sophisticated and need liquid cooling, you can cool them using flow of liquids. Sometimes if the cooling needs to be much higher than what can be done by simple liquids or gases, then you sometimes allow boiling refrigerants to flow over these chips, so that the latent heat of vaporization absorbed from the surface increases the heat transfer coefficient. So the value of H can vary from, let us say, 5 to 20 in the case of air that is not moving at very high velocities, and maybe up to 100 if the airflow velocities are high, watts per meter square Kelvin for air or gases. For liquids, water, etc., the same range can be slightly revised. So this can be something between, let us say, 20 to about 1000 watts per meter square Kelvin for liquids. Okay, and if it is boiling, it can go up to 10 to the power of 3 to 10 to the power of 5 for boiling and condensation. So this is the value of H that has these ranges. And for example, if you are talking about a simple device like desktop PC, you may not probably be able to do a liquid cooling or boiling and condensation. You might want to depend only on the airflow, and therefore you can at most go to a heat transfer coefficient of about 100. So the TS has to be restricted to a certain value in order to avoid damage to the component. So usually this temperature upper limit is of the order of about 50 or 60 degrees Celsius, about 15-20 degrees higher than ambient temperature, and the ambient temperature is going to be critical. So the difference between these two is going to be a critical one. So in summer, for example, if the ambient temperatures can be as high as 30-40 degrees Celsius or 45 degrees Celsius, then the difference that you would have available would be very small, in which case this A has to be substantially increased in order to provide for additional heat transfer. The same thing happens with engines of two-wheelers, for example, most of the engines of two-wheelers are air-cooled because the weight has to be kept minimum, and radiator is too complicated to incorporate into a two-wheeler. Only very high-end two-wheelers have water cooling, otherwise it's all air-cooled. So you have fins on the surfaces of two-wheeler engines. Similarly, you might have seen electric motors. You have additional protrusions on the surface of the motor. So if this is the casing of the motor, you will have protrusions that are jutting out in order to increase the surface area for heat transfer. And normally this is surrounded by a cowling on one end, which is rotated by there is a fan that is rotated by the motor shaft itself, which blows air over these fins in a motor. This is something that you might have seen. If you have not seen it, you can go and take a look. So this is what we call as extended surfaces or fins, which is also part of most of the heat sinks that we use for cooling of electronic equipment. So we can see some illustrations of some of these systems in the pictures that I'm going to show just now. This figure shows the fins on the top of an internal combustion engine, a two-wheeler engine, which is commonly used in motorcycles, etc. So this these extended surfaces, what you see inside is the cylinder piston. This is the cylinder inside which the piston moves in and out, and the crankshaft will come below this. The piston is connected through a connecting rod to that, and the heat dissipated from the surface is taken away by these fins, which are made of aluminum, which is a high conducting material, and air is blown over this by the rotating wheel, and that cools the fins and removes the heat from the engine. Similarly, for electric motors, so this is a typical diagram of an electric motor. So you can see the fan that is attached to the shaft on one end of it on this side, and the cap that is there covering it, which is going to come on top of this, will ensure that the air that is blown by this fan is blown over these fins. Okay, so the air will come from the gap between the cap and the fan and then the motor body. So through this gap, the air will come and flow over these fins and take away the heat that is generated by the electric motor. Right. So this is another picture, which is a cut open view of it. So you can see that there is a fan that is here, and there is a cover. The air comes in from these grills on this side and gets whirled around by the fan and goes out from this to the fins, which are on top of the electric motor, to cool it. The third is the heat sinks. So here is a CPU, AMD CPU that you can see, on top of which this aluminum heat sink is stuck, and then on top of which there is a fan which is kept. This blows air, takes atmospheric air and blows it over these fins, and the air cools those fins and goes away from the sides of the fins. So more examples of the fins are these. So these are multiple pin fins, these are multiple flat fins, these are also flat fins but with a varying gap between them, and this is a typical heat sink that is placed on a circuit board. The whole circuit board has a heat sink on top of it there, and this is one of the processors that has a heat sink. So, and this is another example where this is a liquid cooled system where water can be made to flow through these pipes and the cooling can happen. So that is the example of fins that are cooling the systems. So now coming back to the presentation, the way the fin works is that there is a base body which has a certain high temperature, and this fin is an extended surface which is going to go on top of this. So there is a base temperature TB, and this fin is cooled, and therefore the tip of the fin is at a lower temperature than the base, and you will have a temperature distribution which goes something like this. because the higher the temperature difference, larger is the heat transfer coefficient, and therefore the more rapid is the fall rate of the temperature. But the lower the temperature and the closer it is to the surroundings, the lesser is it. So the slope of this temperature versus x curve will go on diminishing like this. This is the way it goes. So you can see that up to here, for example, the fin is reasonably effective in removing heat because there is still a change, but here it becomes reasonably flat. So this length of the fin actually is not so useful to increase the heat transfer. If the length of the fin is up to here, let us say a certain length L1, up to L1 the fin is able to effectively remove heat, but another additional length of L1 added here is hardly going to increase the heat transfer by 1 or 2% or a few percent. So that's the way this shows. So there is a science that goes into it, which basically has to say what is the upper limit of fin size beyond which adding more material is going to be useless. So this is a principle. The principle is called the fin efficiency. So how well is the material of the fin used to lose heat is a fin efficiency. So this number is a number between 0 and 1. Fin of 0 length, of course, has eta equal to 1, that's of no use to us. But the fin efficiency is high when it is short and goes lower when the fin goes longer. There is another term called fin effectiveness. So fin effectiveness is the factor by which the heat transfer is enhanced by the presence of the fin. So heat transfer with fin by heat transfer without the fin for the same configuration and the same base temperature. If the fin is removed, then what will be the heat transfer? That will be only from this area. And if the fin is present, then the heat transfer will happen from the entire area. So the ratio of these two is called the one number effectiveness, which is a number always greater than 1. So the higher the effectiveness, the better is the fin. But if the fin is infinitely long, it will be higher and higher effective, but its efficiency will go lower. So a good fin is where the effectiveness is high without too much of compromise on efficiency, and these are the two figures that we normally go with in the design of fins. And in selecting heat sinks, normally there is one parameter called R, which is the thermal resistance of the heat sink, which is defined as the delta T divided by Q dot. And what is the delta T and what is Q dot? This is the surface temperature minus the ambient temperature. So the surface temperature which is tolerable for a particular component or a device is Ts, and T infinity is the temperature of the cooling medium, and Q dot is the rate at which the heat needs to be dissipated from that device. Say for example, if it's an electric motor whose efficiency is, let us say, 80%, and it's a, let's say, 2 HP motor. So 2 HP is 1.5 kilowatts approximately, and it's a 80% efficient motor, which basically means that 20% of that energy, which is about 300 watts, is dissipated. So Q dot will be 300 watts. And the surface temperature that is tolerable for a motor, depending on the kind of temperatures of the windings for which the surface temperature would be some value, you can decide on that. So let us say this value is something like 60 degrees Celsius and this value is, let us say, 30. Then the thermal resistance of the fin surface that you need to have is 60 minus 30 divided by 300, which is about 1/10.1. So that is the kind of thermal resistance that you need. But this RTH is more commonly used for heat sinks. So if you have a chip that needs to dissipate, let us say, 20 watts, and the upper limit of this temperature, let us say, is 50 degrees Celsius, and the ambient temperature is, let's say, 30 degrees Celsius, then it is 20 by 20, which is approximately 1 degree Celsius per watt. This is the unit for the thermal resistance that we look at. The fin that you need to put on top, that is the heat sink that you need to put on top of the chip, needs to have a minimum thermal resistance. The thermal resistance at most, the maximum thermal resistance has to be this. It has to be lower than this. Only then will this sink suffice for maintaining this temperature permissible for this kind of the heat liberation in that device. So normally commercially available fins in the market come with their own value of R, and one can select the fin with the appropriate R by looking at what is the permissible temperature difference and what is the heat loss or heat dissipation that needs to be taken care of by that heat sink, and using that you can select among the various varieties that's available in the market which one you need to buy. Right? So that is about extended surfaces and fins. I have uploaded more material on Moodle, so I would request you to take a look at it and come back. So that will close the topic on steady state heat conduction. So I would like you to study both these lectures carefully with the uploads that I have put on Moodle. I have put copyrighted material on Moodle, and therefore please don't share it with people in public, but at the same time make sure that you make best use of the available material that is given to you. So we'll close here. The next lecture will start with study of transient heat conduction. That's another nice science in itself. We'll look at it when we look at transient heat conduction. So we'll stop here. See you again.